Okay, good afternoon, children. Today we are doing valence bond theory for covalent bond formation. Uh, so let us first consider the simplest molecule. This is the simplest molecule, hydrogen, and we know there is a covalent bond between the two atoms in hydrogen. So how is this covalent bond formed according to valence bond theory? That we have to look into. The hydrogen atomic number 1, its configuration is 1s1. So, so this is the hydrogen nucleus, and this is the 1s orbital of hydrogen, and this 1s orbital is half filled, one electron is there, and probability of finding electron, these dots are telling us the probability of finding electron. Then there is another atom of hydrogen, so its nucleus, and this is its 1s orbital. It is also half filled. It is the probability of finding electron. Now, according to valence bond theory, what happens is these two atoms of hydrogen, you see it is looking slightly bigger than this, but they are same. According to valence bond theory, the two atoms of hydrogen, they gradually come closer. They gradually come closer, and at one position, as it is coming closer, it will become like this. So you see at this position, the probability of finding the electron, is much more in between the nucleus. In between the nucleus, the probability of finding electron is much more, and there will be now more force of attraction. There will be more force of attraction, and covalent bond is said to be formed. Covalent bond is said to be formed, and this is the covalent bond that is formed. So, according to valence bond theory, a covalent bond is formed by overlap of half-filled atomic orbitals of the participating atoms. Now let us consider another molecule, say O2. So oxygen molecule, how is oxygen molecule formed according to valence bond theory? So oxygen atomic number 8, we know its configuration is 1s2, 2s2, then 2px2, 2py1, 2pz1. This is the configuration of oxygen. So here we see this is the outermost shell orbitals. These are the outermost shell orbitals, and we know that outermost shell orbitals or electrons take part in bonding, and out of that only this one and this one is half filled. So they are in the outermost shell, but they are not half filled, so they won't take part. These orbitals won't take part. Only 2py1 and 2pz1 will take part because they are half filled. So let me draw this orbital. So suppose this is oxygen atom nucleus. This is another oxygen atom nucleus, and suppose this line joining the two nucleus is called internuclear axis. Internuclear axis, and suppose this internuclear axis happens to be the y-axis. This internuclear axis happens to be the y-axis. So, I am drawing this PY1. P, it is dumbbell. P is dumbbell, and P of another oxygen atom. So this 2py having one electron half filled, this 2py of another oxygen atom half filled, they have overlap head on, and this overlap, so this is the overlapping region, has resulted in formation of a covalent bond. Now, what about this 2pz, which is also half filled? Now 2pz will be this one. This is 2pz. This is also 2pz. So this 2pz, let me write it down. This is 2pz. This is also 2pz. Obviously, they will be parallel to one another. They are parallel to one another, and these two orbitals are also very close. They are very close. Actually, these two p orbitals are like this. These two p orbitals are actually like this, and you see they have overlapped, but overlapping here and overlapping here is different. This is head-on overlap, and this is called sidewise or lateral overlap. So this is the overlapping region. And this sort of overlap results in pi bond. This pi bond, also known as p-pi bond is also known as. Though here Z is involved, then also this is called this is called p-pi. So pi bond, or simply p-pi bond. Now, how to show that this p-pi bond in this diagram? As I already said, this p orbital are not so far. They are close. They are very close, and that overlap we show it by drawing like this. So this is our O2 molecule. And after that we can draw it like this. O, a double bond. The bond formed by head-on overlap is called sigma covalent bond, and the bond formed by in this way is pi covalent bond. And these two electrons, which are also outermost shell, they will be present as lone pair. So this is how O2 molecule is formed according to valence bond theory. Now, coming to the case of N2 molecule. So N2 molecule, if we do in this way, we will see that there is a N triple covalent bond. There is N triple covalent bond, So first of all, let us write the electronic configuration of nitrogen. Nitrogen is 7 atomic number. So its configuration will be 1s2, 2s2, and according to Ohm's rule of maximum multiplicity it will be 2px1, 2py1 and 2pz1. So all these are orbitals of the outermost shell, but as you can see, this one and half filled. 2s is not half filled. So so in nitrogen molecule, what will happen is like if I continue from there only for shortcut, so I have to draw another p orbital, and that p orbital will be as, since px, py, pz are mutually perpendicular, that I will draw it like this. This is another p orbital. So this is another p orbital. So suppose it is px. Suppose it is px. This is px. So px and px will also overlap sidewise, and another pi bond will result. So that we can show it like this. Okay, that we can show it like this with double line. So this is nitrogen molecule. So what we are seeing is nitrogen molecule is having a triple covalent bond, 1 sigma bond and 2 pi bond, and this 2s electron is not used in bond formation, so it will be there as lone pair. So this is nitrogen molecule. Okay, now now let us consider the case of molecules of compound. Okay, so let us see the formation of CH4 molecule. You can easily understand in CH4 there will be 4 bonds, and it is seen that experimentally it has been seen that all the 4 bonds in methane are equivalent, and the shape of methane has been found to be a tetrahedron. This is tetrahedron, it's 3-dimensional molecule. Let me tell you is that all these lines are not covalent bond. Which are covalent bond? This is a covalent bond, this is a covalent bond, this is a covalent bond, this is a covalent bond. And other lines has been drawn to give this information. For example, this line tells us that this hydrogen atom and this hydrogen atom is above the plane of the bore. This hydrogen atom and this hydrogen atom is which has been joined by a broken line. It means that it is behind the plane of the bore. This carbon atom is on the plane of the bore, and this lines has been drawn to complete the tetrahedron. And you know, in tetrahedron all these angles are same, and the measure of the angle is 109 degree 28 minutes. So all these facts we need to explain. So let us do this like this. First of all, since central atom is carbon, so carbon ground state configuration 1s2, 2s2, 2px1, 2py1, 2pz0. The ground state configuration, and so here you see there is no electron. Now as you can see, since we require formation of 4 bonds, and here we are having only 2 half-filled orbitals, what we have to do here, we have to take this carbon atom in excited state. Excited state. This is ground state configuration. We have to take it to excited state configuration, means a higher energy state. So in that case, this electron will go to empty to pz. So this is the excited state configuration. So now you see we have 4 half-filled orbitals. Now these 4 half-filled orbitals can give rise to 4 bonds. But one more thing is, since all these 4 bonds are identical, these orbitals as such doesn't take part in overlap. This orbital doesn't take part in overlap. Before overlap, a phenomenon takes place that I'm going to tell you here. Before overlap, these 4 orbitals, what they do, these 4 orbitals, they mix together. They mix together and new set of 4 orbitals are formed. So s orbital, px orbital, py orbital, pz orbital, these 4 orbitals, they mix together and a new set of 4 orbitals are formed. So those 4 orbitals, I am drawing it here. So say this is one orbital, this is another orbital, this is another orbital, and fourth one is this one orbital. So 4 orbitals, 4 atomic orbitals mixing together, new 4 orbitals are formed. Now what is the name of this orbital? This orbital is called sp3. sp3. Why sp3? Because it has resulted after mixing of one s orbital and 3 p orbital. That's why sp3. And it is called sp3 hybrid orbital. sp3 hybrid. Similarly, this is also sp3 hybrid. This is also sp3 hybrid. This is also sp3 hybrid. So all these are sp3 hybrid orbital, and all these orbitals, will are identical. Here, it became a bit narrow. This one broad. It is not like this actually. All the orbitals are have same appearance, and each of these orbitals are half filled. Each of them has 1 electron, so they can now overlap. So suppose I am showing that electron here, 1 electron. Each of them has 1 electron. So they can overlap with hydrogen. Hydrogen, has atomic number 1. Its configuration is 1s1. 1s1. So they will overlap with 1s1 of hydrogen. This is 1s overlapped. This is 1s overlapped. This is 1s overlapped. 1s overlapped. So now you see all these bonds will be identical, because this bond has resulted by the overlap of sp3 hybrid orbital and s orbital. sp3 hybrid and s. sp3 hybrid and s. sp3 hybrid and s. So all these bonds are identical, and in this way we can explain the equivalency of the 4 bonds in methane. And here also the angle will be seen as observed one. We can explain the angle also. These hybrid orbitals, these sp3 hybrid orbitals will make an angle of 109 degrees between them. So you see, uh, this, whether I have said or not, this mixing of atomic orbitals to form hybrid orbital is called hybridization. So this is a very important topic, hybridization, a very important concept, hybridization, and we say that carbon atom in methane it is sp3 hybridized. Carbon atom in methane is sp3 hybridized, and this is called orbital diagram of methane. Now, in the same way, you can draw the orbital diagram for, say, ethane. Ethane is C2H6. Ethane is C2H6, and you know, in ethane also carbon atom is sp3 hybridized. You try to make the orbital diagram of ethane. So in case of ethane, where there are two carbon atoms, you see this is another carbon atom, and it's also sp3, 4 sp3. These are the 4 sp3 hybrid orbitals of carbon. They are also directed at this angle, 190 to 28 minutes. All of them are half-filled orbital, so they are going to overlap with hydrogen, and in this way sigma bond is formed. And what is this bond? This bond has been formed by overlap of sp3 carbon of this carbon atom and sp3 of this carbon atom. So this is how this is formed. So this is the orbital diagram of ethane. Now I'm sure in this way you can make the orbital diagram of other hydrocarbons like propane or butane and so on. Now you must know this thing. What is the difference between